All right, hi everybody. So this is going to be section 3 of chapter 6. We're going to go over a couple of different pieces of information about ionic compounds. We're also going to talk a little bit about ionic bonding. We're going to talk about strategies or theories behind lattice energy, how to determine how strong lattices are, and what it means to have a lattice. We're going to talk about the difference between ionic and molecular compounds as far as like physical properties are typically concerned. And then we're finally going to end up talking a little bit about polyatomic ions. You do have a separate assignment around polyatomic ions to work on. Okay? All right, so first things first, ionic compounds are going to be defined by what they are made of. And typically, they are going to consist of positive ions and negative ions that are literally only held together by the attraction that they feel for each other. So since opposites attract, positive and negative tend to attract as well. Okay, and up here we see an example of table salt, so NaCl. It has a sodium ion and a chloride ion. Now, sodium tends to form a positive ion and chlorine tends to form a negative ion. And because they have those opposite charges, that's why they're attracted to each other. So we can define an ionic compound as something that is composed of positive and negative ions that are going to be combined in such a way that the number of the positive charges and the number of negative charges are going to be equal and opposite of each other. Okay, from there we can talk about how our ionic compounds tend to exist in what we call a crystalline form. And this is where this idea of a lattice energy comes from. So a crystal is literally defined as a three-dimensional structure where positive and negative ions are, in which they separate themselves so that they are optimally bound together. And by optimally, we mean that a positive ion is surrounded by negative ions and that negative ions are surrounded by positive ions. Now, the difference between this and, say, a molecular compound, which is one we're going to talk a lot more about and that we talked about in section 2, the ionic compound is not going to have independent units that can be isolated. So, for instance, if I zoom in on a salt crystal, I cannot remove NaCl. I will remove Na particles or Cl particles that are ionically charged. In a molecular compound like sugar, if I tried to, I could remove a single unit of that particular type of compound. So for instance, sugar has a structure C6H12O6. If I zoom in at the molecular level and I want to remove one molecule of C6H12O6, I can. That is not going to have attractions for other parts of that compound. It's going to, easily come apart. Okay, so that's one difference between the two. Another thing that we can talk a little bit about is how we talk about ionic compounds. So with molecules, we say CO2. Okay, we say that is the formula of the particular compound we're talking about. It is molecular in nature for a lot of reasons, one of which is it's made up of mostly nonmetals. And those particular molecules, if I zoom in or I want to look at the pieces of this particular compound, I would see multiple pieces that have a carbon and 2 oxygens. That's a CO2 molecule by definition. Now, an ionic compound has what we would call a formula unit. So it's more of an ordered structure. We say the formula unit is going to be like the lowest ratio of the different types of ions that are in the actual compound. So for instance, NaCl, the formula unit is NaCl. For every one Na, you'll find a Cl. And that is how we describe our ionic compounds using that particular type of formula that we've discussed in the past. Okay, and so to give you an idea, over here we have the simplest unit of an ionic compound. Will have multiple of those different units. So an A and a B they're going to be kind of interdispersed with each other, where every positive atom has negative atoms around it and every negative atom has positive atoms around it, and so on and so forth. And so this is what we would call a formula unit. If we just looked at the ratio of these things, we would say that for every one of these negative charges, there's one of these positive charges. For a covalent bond or a molecular compound, like we talked about in section 2, for every one of these, there may be one of these, but there could also be 2 or 3, and a single unit can be looked at as a single molecule. And so instead of saying that every single one of these is surrounded by a ratio of this to this, we would say that one of these atoms is bound to one of these atoms, and they form this particular structure over and over and over again. Now, multiple of these little pieces would be found kind of floating around in this particular solution versus this one, which would have multiple of these positive, negative, like clumps kind of floating around. At the end of the day, ionic formulas are going to have ratios, and molecular formulas are going to have small versions that kind of indicate what is the smallest unit going to look like. Okay. So that being said, we can kind of go back and we can discuss our electron dot notation from section 2. A sodium atom is going to have one valence electron, not two. I apologize for that typo. And a chlorine atom is going to have two. So since this sodium atom has one valence electron and this chlorine atom has seven, when these two form a compound, what happens is the sodium atom gives up its electron to fill the chlorine atom's octet. And when that happens, since this thing has lost an electron, it becomes positively charged. And this thing gains an electron to become negatively charged. Now, the cool thing about this is this describes how ions are formed in general on the periodic table. So if it's in group 1, it has one valence electron. If the atom you're talking about is in group 1, it has one valence electron, and it will have no problem losing that one electron to bond with something that will take the electron on, like this particular chlorine atom, which is in group 17. So group 17 atoms and group 1 atoms tend to bond together in an ionic manner and form what we call salts by giving up a single electron from the group 1 atom to the group 17 atom in order to form the full octet around chlorine and to get closer to the noble gases formation of the previous row for the cation that forms. In other words, if I went through and I looked at the electron configuration for sodium, I would get 1s2, 2s2, 2p6, 3s1. Giving up that 3s1 makes my configuration 2p6 at the end, which is, of course, the gas neon. And I don't know if you remember me saying this in chapter 5, but everybody wants to be a noble gas. Everybody has the goal of being a noble gas or having a noble gas configuration to live with. So chlorine wants to gain that one electron because when it does, it becomes the nearest noble gas, argon. It has a full 3p shell now when it gains that one electron. This describes why our atoms form the ions they do on the periodic table. And so you may or may not be familiar with this in the common ions that are formed on the periodic table. The reason they're formed the way they are has to do with how many electrons they either give up or gain based on their electron configurations. Okay, so that brings us to this idea of a crystal lattice. Now, when ions organize themselves into a lattice is kind of like a really highly ordered network that ideally separates negative and positive charges from each other so that they're at optimal distances, if you will. And what we do is we see this same idea of minimizing potential energy by creating the most orderly arrangement we can. When it involves ionic compounds, we call it a crystal lattice. When it involved molecular compounds and two electrons sharing in a bond, we called that a covalent bond. Now, in this particular case, this crystal lattice has a couple of things we have to describe. First is going to be the attractive forces that the positive and negative charged ions are going to feel for each other. Remember, the opposites attract idea. There's also going to be repulsive charges that exist between things that are similarly charged. So those things that are similarly charged have to be kind of optimally distanced from each other in order to create this ordered lattice structure. Now, the combined things between the attractive and repulsive forces, when you add them all together, just like we did with our covalent bonding, these combined forces form that crystal lattice, and they are going to determine a couple of things. The first is going to be the distance between the different ions, so positive and negative, and the other is going to be the pattern of the arrangement within the actual crystal itself. So here we see sodium chloride and cesium chloride, two very different ionic compounds. You can see that there are positively charged atoms that are pretty small and they're kind of ordered throughout. If you took a cross section of this, you would see a very, very ordered pattern. Same thing with cesium chloride. This is what we call a formula unit. So in other words, I could take many of these boxes and I could stack them next to each other. They would all just kind of overlap. And we'd put that one cesium ion in between all of them. Again, this lattice is determined, or the structure of the lattice is determined by the attractive and repulsive forces within that ionic compound. Okay, so that being said, we have a comparison where we talk about the difference between ionic and molecular compounds. So the forces that hold ionic compounds together, unlike molecular compounds, ionic compounds are held together by that electrostatic attraction, so the opposites attract idea. In molecules, the attractive forces and the repulsive forces that are at play are going to be a lot weaker. Now, that being said, the idea behind molecular covalent bonds instead of ionic compounds, in molecular compounds, the fact that they share electrons and not just give them up makes it a stronger bond to deal with. Now, so we can't just discount it, right? We can't just say that one is stronger than the other and that's the end of it, and that it's super easy to break one over the other. If it was super easy to break any of these bonds, we wouldn't exist the way we exist, because the bonds that keep us together are the same types of bonds that we're studying in this class. So the difference in the strength is going to be the thing that is based on a couple of different factors. Most of the time, it just kind of comes down to that final idea that if we want to have a very strong attraction, we should have units, as far as ionic compounds are concerned, that have to do with the opposites idea, right? So if we want a strong attraction to occur, the stronger the charge difference, or the stronger the attraction, the more the strength of that particular ionic compound is going to be. Same thing with molecular compounds. The strength of attraction in molecular compounds is going to have to do with the types of atoms that are attracted to each other, if they're the same type of atom versus different types of atoms. Okay, so some things that we want to know about molecular compounds versus ionic compounds. So molecular compounds tend to have pretty weak forces between the individual molecules, which means they melt at lower temperatures. When we talk about individual molecular bonds, we're saying relatively weak forces. We're saying weak compared to an ionic compound. We don't mean weak in general, like it's super easy to break them. We mean weak compared to ionic compounds. Now, ionic compounds are very strong compounds. If they weren't, they would not be solids at very, very high temperatures. So ionic compounds tend to have really, really high melting points. You have to put a lot of energy in the form of heat in to get them to change their phase. And a lot of times there are ionic compounds that just won't melt. They'll just break down altogether instead of melting. They tend to be pretty hard substances that are easy to break. So a hard substance is easy to break if it's what we call brittle. And what that means is if you are trying to break it, you can, but if you push on it, it shouldn't break into like tinier and tinier pieces kind of thing. They're not very good electrical conductors when they're solids, but if we put them in solutions, they become really good conductors. So think about them as far as like salt water versus non-salt water. Saltwater compounds, or salt water itself, tends to conduct electricity because the ions separate when they hit water, and then they can conduct electricity themselves. Okay. All right. Okay, so here is our first lecture question. I want you to describe one difference between a molecular and ionic compound. Just pick one and describe the difference between the two. When you're done with this question, so you can pause it now, or you can move on. When you're done with this question, go ahead and move on. Question number 2 is going to be, what is a crystal lattice? So tell me what a crystal lattice is when it comes to ionic compounds. Again, you can pause it to answer your question, and then when you're done, go ahead and move on. Lecture question 3 is going to be to describe the difference between a formula unit and a molecular formula. We talked a little bit about this at the beginning of the lecture. All right, when you are done, you can go ahead and move on. Okay, so we have one more topic that we're going to talk about, but before we do that, I do want to show you some ionic versus covalent compounds and some of the features and or physical properties that each one experience. So over here on the right, you can see that melting points are pretty high, triple or quadruple digits, melting points in Celsius versus Kelvin. For ionic compounds, like we said, they're going to have really high melting points, which also means they're going to have pretty high boiling points compared to our covalent compounds, which have relatively low melting points as far as those are concerned. Okay, and the last topic we're going to talk about is just a polyatomic ion. So polyatomic ions are just going to be a type of molecule or ion, if you will, that has both the characteristics of molecules and ions. Polyatomic ions are so common in our environment. I think you would be shocked if you wanted to learn more about it. And you will learn more about it, don't worry. We're going to study these a lot in the next chapter. For now, what I want you to realize is that polyatomic ions are just going to be groups of covalently bonded atoms that have a charge. So if you remember back to our section 2 activities on Lewis structures, anytime you were drawing a structure that had a negative charge in it or a positive charge in it, you were likely drawing a polyatomic ion. If it had more than one atom and they were considered covalently bonded, which is why we drew the Lewis structures, that is referred to as a polyatomic ion. Now that ion itself is going to have a charge based on whether or not it has excess or a shortage of electrons. Okay, and with that, what I'm going to have you do is our last lecture question, which is just, what is a polyatomic ion? When you are done with this, you are done with this particular lecture. You have, make sure that you are writing those questions down. So maybe make sure you label them 1, 2, 3, and 4. Make sure you have your descriptions ready to go so that you can just enter them into your quiz that you're going to take on Monday over these lectures. Okay. Have a great day.